Okay, so thank you very much for the invite to speak. Very unusual in speak. So I am the professor of neuroscience here. That means I have an interest in aging and in trying to preempt the aging process to essentially stop or slow down the development of chronic diseases of aging with a view to increasing the years of healthy living we have. So the neuroscience approach is not to try and make people live indefinitely, that's science fiction. But essentially we can give ourselves more years of healthy living. And to start with, I suppose for this audience, we'll start with Charles Dickens' A Tale of Two Cities. It was the best of times, the worst of times, an age of wisdom, an age of foolishness. It is the best of times because today more people live beyond the age of 60 than at any other time in human history. So we are doing something right. Unfortunately, it's the worst of times with war in Europe yet again. And an age of wisdom, we have suddenly discovered that aging is malleable. So we can slow down the rate at which aging progresses and when we have the onset age-related diseases. It also is the age of foolishness because a lot of the materials that we need to slow down the aging process and improve our age-related health come from the natural world, and we're absolutely destroying. The cost of treating age-related diseases is staggering. So pre-COVID, it was estimated to be $47 trillion in 2010, 2030. So as a fundamental lab scientist, that kind of number is almost incomprehensible, but it does draw the attention of governments, and it draws the attention of pharma. The economic impact of socioeconomic inequalities associated with age-related health is again absolutely staggering. It's disgraceful. It's around 1,000 billion euros per year, 9.5% of GDP. And essentially, the impact and the cost of our age-related health is amplified by social deprivation. And if you look at regions of the world where the global population that ages, those over 60 is increasing, I think the term used earlier was the developing south. But essentially, it's in less developed regions of the world. It's certainly not in Europe. It's not going to be in the US. It's not going to be in Japan. And it's the regions of the world that can least afford it that are really going to take the hit. And what happens is you're going to get the appearance of a diseasome of aging. So a range of very, very different diseases. So chronic kidney disease, cancer, diabetes, heart failure, all very different diseases, but they are all underpinned by a dysregulation of a common aging process. And that aging process is affected by that changing environment that I mentioned that we're destroying. So we have a diminution of our stress defenses internally as we get older. We have a change in the microbes that live in our gut. We have an inflammatory burden that accompanies all those diseases I've just pointed out, and we have a loss of physiological resilience. And those features and how we deal with them and the factors that actually drive that loss of resilience are all related to our changing planet and the destruction of our environment. Now, for Scotland, this is also important. We're meant to be part of a developed nation, but Scotland is the sick man of Europe. Glasgow is the sick man of Scotland. And if you look here, if I can see both with an arrow, no. So the red dot on the left-hand side is the death rate per 100,000 in Scotland. Just above it sits Albania, below it sits the rest of Europe. So Scotland's not doing very well. If you go to the right-hand side and you look at Scotland broken down by council area, most council areas do quite well, but the picture is skewed at the top by the east end of Glasgow. So there we have, oops, back, now, a much higher death rate in some areas of the east end of the city. This is it's disgraceful. The difference you're observing between here in the east end and here at the bottom of Lindsay, where we have on average the best life expectancy or a male in the planet, within a 12-kilometer geographical radius. It's a bit scary. And that difference is tied to a very steep socioeconomic gradient between the east of the city and Lindsay, and then the sequelae of ill health that's manifest in the East End. So we need to understand why diseases typically associated with old age are appearing at earlier ages next to the city. And therefore we need to understand the aging process. So Oscar Wilde's approach, being Irish, I like Oscar, I had him when I was at college. He said to get back into youth, you do anything except take up exercise, get up earlier, be respectable. It's almost a sort of a teenage approach. I don't necessarily agree with it the way I would like to. It's a relaxed approach, and psychology is a big impact on how we age. I'll come on to that in a little minute. But more importantly, you can think of aging as an accumulation of deficits taking place, different individuals, different rates, different ways. But it starts pre-conception, which may surprise you, and it ends death. It's not passive. It's actively regulated by biochemical pathways. So if we can understand the molecular basis of those, we can manipulate them, and we can improve the number of years of healthy living that we have. So in essence, this is the Shields aging trajectory, age 10, 30, and 60. And you will age differently from age. I almost think of Tolstoy and Anna Karenina. All happy families are alike. Each unhappy family is unhappy in its own way. So we all age like an unhappy family. Different factors of patients differentiate. We can now use molecular and cellular biology to hallmark aging into features that are common to yeast, to worms, to mice, flies, and now humans. And those hallmarks, I'm not going into the technical details of it, but they are the targets for manipulation. It's important to understand that we can manipulate those, because if you cure cancer or heart disease, it's estimated you can only add 2 to 3 years of healthy life expectancy to a 50-year-old woman. Whereas if you could manipulate the underlying aging process, you could probably add an extra 25 years of healthy life. So when you have the disease, you've accumulated a lot of wear and tear already. So what you have to do is slow down the rate at which you accumulate the wear and tear. Now, we're very sophisticated now in terms of the molecular and cellular biology of aging and how we understand it. But I'm going to show you a crude analogy. You think of your body like a car. Where we are at the moment is that if a bit goes wrong, we can tend to fix it, put a sticking plaster on it, essentially. But what we can't do is deal with this. Put your car in the wrong environment, in the wrong place, at the wrong time, it gets trashed. And that's the effect, really, of your exposome, or the environment that you place your body in. And the exposome was a term developed by Conrad Wilde that states that it comprises the totality of human environmental exposures, both biotic and abiotic, preconception to death. So that is where you live, how you live, what you put into your body, how you get on with others. And to emphasize its importance, 3 simple exposure factors account for 50% of mortality annually globally. That's air pollution, tobacco smoke, and diet. And myself and colleagues have tried to develop an appreciation of how the exposome affects how we age. We've used the kidney to model that, really need to focus on. But essentially what you're looking at here is how we're trying to understand how genetic and epigenetic factors interplay with your lifestyle, your socioeconomic position, your psychology, nutrition, and wider environment when you're young. So that's, and then how they work against you when you're older to remove, oops, this is jumping, physical capital. So essentially the black line here on that graph is a good trajectory of aging. You peak when you're sort of ready to breathe and you're fit and healthy. And then over time, normally from beyond the age of 40, you start to lose physical capital. The red line is essentially someone with a poorer trajectory of aging. They lose physical capability faster as they age. What we're trying to do is get that red line back up towards the black, so you have more years of healthy living in old age. But also bearing in mind, when we try to do this, what's good for you when you're old is not necessarily good for you when you're young, and vice versa. So we need to know where to intervene most appropriately to improve health. Do we need to get all the measures in place when you're young, or can we do it in middle age, or can we do it in old age? When I started out as a natural scientist, became a molecular biologist, but now I've worked my way back to being a natural scientist, because I'm having to get to grips, usually in cross-disciplinary collaborations, where I'm having to, by force, really to deal with the problem at hand, deal with sociologists, clinicians, other scientists, public health officials, and the public, to understand how our environment, when we are a child, leads to specific adult health outcomes. So, try to understand how, when you're young, your environment, and certainly your household environment, impacts on your health. Are your parents nurturing and supportive, or are they abusive? Do you get support from your wider family and community? Do you live in a threatening or a non-threatening environment, etc.? And that concept of an exposome allows us to narrow down individual features that we think we can manipulate to improve age-related health. So currently, medicine tends to treat the diseasome of aging as individual different diseases. And when you treat them, you get a small improvement in health span or years of healthy living. Whereas if you could target that underlying component of the aging process, then you may be able to preempt or slow down the onset of the individual diseases and compress the period of ill health at the end of your life into weeks and months, instead of 10 to 15 years of health, which is currently what happens. So this is the Glasgow Exposome. If we compare affluent and deprived areas of the city, those living in deprived areas tend to have a greater body mass index, they have an imbalanced diet, they are more inflamed and tend to be more sedentary. The affluent tend to be leaner, have a balanced diet, exercise more, and have fewer miles on the clock when we actually measure how they age biologically. We've also found that you gain more miles on the clock if you live in an environment that you perceive to be threatening. This is especially true of women. And there have been, and lots of reports showing that there are adverse health consequences associated with it. The big surprise for us was that as you age, you become more inflamed. And therefore, in clinical studies and laboratory studies, the correlation between the degree of inflammation that you have, the number of miles you have on the clock, correlates very strongly. But you went to the Glasgow general population, and that variation biologically, so the miles on the clock, only explains about 10% of the inflammation. That was a big surprise. So we've tried to track down what's driving the inflammatory burden in the population, and that brought us back to nutrition and the gut. So, as we mentioned earlier, Hippocrates, he's misquoted as saying let food be thy medicine. What he did say was something completely different. It was, I think, there are two things: science and knowledge. One begets ignorance, and one's opinion, the other begets ignorance, and the other helps us move forward. Diet's really important. So the Lancet Commission has already, shown us that it's attributable to about 22% of deaths globally annually, and it may be the single and most simple lever to manipulate and optimize human health. So many humans think we're carnivores. We have descended from frugivorous ancestors. Our gut is designed to be omnivorous, independent of whatever choice we make of what to eat. Our biology tells us we're omnivores. Most of us think we're carnivores. And if you go to the natural world and you look at how carnivores age, well, big cats are obligate carnivores, only eat meat. And they tend to basically die of kidney disease if they're not predated upon by others. So even domestic cats, more than 3/4 of domestic pets will die of cats will die of kidney disease. 50% of these guys will have colorectal tumors. So again, associated with eating red meat. They'll have an elevated inflammatory burden. No surprises. Yeah. They also have phosphate toxicity, which is not a common one. It's not commonly discussed, certainly not in the public domain. But if you're a mammal, the more phosphate you have in your system, the shorter you will live. So you can do it. Here's a graph, and at the bottom here are human centenarians, less phosphate. Standard human, a little bit more. This is a human with Hutchinson's-Gilchrist progeria syndrome. These people have highly accelerated aging. By the age of 15, they will look about age 80. They will die of cardiovascular disease or cancer. But across all mammals, you can see the shorter you live, a rat and a mouse here, for example, you'll have higher levels of phosphate in comparison to humans. That phosphate is acquired nutritionally. So no surprises then when you go to look at Glasgow. Cheap red meat is a common feature found among our most deprived, typically our meals. And it's associated with accelerated aging and poorer kidney function. I'm not going into the technical details of that, but just like the big cats, if you eat too much red meat, you will have poorer renal function. You'll end up with renal disease. You'll end up with colorectal cancer because, again, our population in Glasgow shows that those that eat red meat 5 or 6 times a week have a higher incidence of colorectal cancer and poorer renal function. Amazingly, the general population, there are many running around kidney function that's equivalent to mild to moderate kidney disease that's really going undiagnosed. But, you can understand why there's a link between the function of your kidney and the function of your heart. Glasgow is an epicenter for cardiovascular disease. So, simple fixes. It's a no-brainer. You've got to change where the protein you take in comes from. And replacing animal protein with plant protein will help. That should reduce the rate of cancer-related, cardiovascular-related mortality. And indeed, when you start with the big numbers, the UK Biobank studies looking at hundreds of thousands of people, you get support for that. The other thing, eventually we get to the microbiome. Red meat brings in carnitine, and carnitine is broken down by bugs in your gut to generate a compound called PMA that's highly pro-inflammatory. We do not have the capacity to generate PMA. It comes from the bugs in our gut. And in recent years, we've found that breakdown of carnitine to TMA by bugs in our gut is associated with cardiovascular disease and the inflammatory burden associated with that. It's also been associated with chronic kidney disease, again, just as we see in Glasgow, and more recently with arthritis. Interestingly, if we look at the Glaswegian population, the bugs that make PMA, which is then processed in your liver, I think called PMA, it was even worse. On the same biochemical pathway, there's a branch, and the branch makes a thing called beta. And beta-ine is a component that puts methylation on your DNA. And methylation is used like a dimmer switch in your genes. It tells them what level to work at. It's also got a timer attached to it. It's where to work, when to work, what level to work at. So it's part of maintaining your epigenetics. And if we look at the Glaswegians, are deprived that show the accelerated aging of less of this in their system. And we've asked, is that due to potential differences in their microbiome as a consequence of dietary? And what we find is, yeah, we can go to those that show the most biological aging, and we can find differences in the bugs. In this study that I'm going to show in a moment, we don't look at living organisms. We're not looking at fecal bacteria or oral bacteria. We're actually looking at bacterial DNA signatures in the blood. So these are things that have got in through your gums or through your gut. Your gut leaks as you get older, and you've got kidney disease, your gut leaks. And your immune system is very good at picking off the bugs that get in. And we can then, have a bacterial barcode, as it were, for what gets in. And what we see is that our deprived have a higher prevalence of a number of pathobionts that have been associated both with oral disease, with pneumonia, potentially with Alzheimer's now. But more importantly, from us having identified the Glaswegians have a poorer renal health, we see bugs that have been associated with poorer renal function. So we have a biologically plausible story emerging. The affluent, well, they have more soluble biomes, so help promoting bacteria. No surprise, these are things like lactobacilli and lactospiraceae chorea. And these guys are important because they can break down phenolic acids in fruit and vegetables. And the product of that breakdown is able to trigger a gene called NRF2, and that controls most of your cytoprotective responses. So about 2% of all the genes you have are controlled by this guy. In response to stress, this comes on and triggers everything to deal with that stress. The Western diet does not support the growth of those submucobiomes very well. They are much better supported by traditional diets, pickle, ferment foods. And if you go to the regions of the world where people live the longest, they're called blue zones. People live happily, over 100. You can get people active and working at 110. So that's Okinawa, Loma Linda, Ikaria. So there's 7 regions. They have different ethnicities, different genetics, but despite different diets, they all still have a very heavily component of food preservation that involves pickling and fermenting. And it's key because our microbiome has evolved with us over the past 2 million years, from when we were these frugivorous apes living up in trees to moving on to the savannah, and we became more omnivorous, tended to eat wild game and berries. But over the past 150 years, our method of food preservation has changed. And we tend to use inorganic phosphates a lot, by the way, to preserve food, which is not a good thing. And the impact that has had on our microbiota has been quite staggering, and we don't know the full ramifications of it yet. But we now have an industrialized microbiota, which is not necessarily good for us. So what we can see with processed foods, there's lots of inorganic phosphate. They can trigger microvascular disease, obviously weight gain, and glucose intolerance is driving diabetes. Not a pleasant picture. Interestingly, we can actually use naturally occurring bioactive substances to bypass those deleterious aspects of our diet and actually trigger NRF2. So we know that NRF2 is diminished as we get older. It's also diminished by a Western diet, smoking, psychological stress. It's promoted by exercise, again, a no-brainer, but also a number of foodstuffs. So eating things like curcumin, broccoli, kimchi, rosemary, black coffee, you see me, I swig lots of it. They all contain polyphenolic compounds that are good for salutogenic bacteria. Interestingly, pharma has jumped in and made drugs to target NRF2. Basically, in the standard pharmacological model, they want a target, a disease, and a drug for it. They don't always work. 2 out of 3 phase 3 clinical trials failed. The naturally occurring substances all appear to work as well as our best pharmacologies. And more importantly, not only do they activate NRF2, we can use them to remove old cells from the body. Now, old cells or senescent cells are causative for disease. You can take them from one system, put them in another body, and trigger the disease. Some of these naturally occurring bioactive substances are called senolytics. They're able to basically cause the destruction of those cells. So this is just an example of using something called ficitin, which you find in grape skins and the strawberry skins, given at the right dose to mice. So on the left is a 2-year-old mouse that's been treated with the ficitin. And on the right is his 2-year-old sister that hasn't. Really, really powerful. So these mice will live a little bit longer than normal, but they will not live indefinitely. But they are healthier for a lot longer. So there's a real drive now to try and get many of these substances at the right dose to people. You will see a lot of rich individuals, as in sort of the Jeff Bezos of the world, taking some of the pharmacological agents to do this, but we don't always know what off-target effects they will have. Whereas with the naturally occurring substances, if we can identify what dose they work at, we can take them safely for a lot longer. We've also gone back into the natural world to look at this, because humans, like the felids, tend to be much more inflamed for kidneys. Bears, on the other hand, can manipulate that switch between PMA and beta naturally. So when they go to hibernate, they will reduce the level of PMA in their system by changing their microbiome. And they do this seasonally. So, for example, if the birds are getting ready to hibernate and you're in North America, they'll start eating lots of salmon. In Europe, they eat bilberries because we don't have the salmon. And they'll eat huge quantities. And the bilberries that they eat, this is a European brown bear in the north of Sweden, they contain lots of these polyphenols that you need to support the good bugs in the gut. Typically, they're associated with bright colors of the berries they eat. Now, what you can do is you can take bear poop from a bird that's getting ready to hibernate. You do what's called a fecal transplant. You take the bacteria in the poop, you can put it into a mouse to see what happens. So this is the mouse that's got the bear poop and the bird that's getting ready to hibernate, and this is its sister. It's a really powerful example of what your microbiome can do to your metabolism. So we tend to think that our metabolism is regulated by our own genes, when in reality, the microbial metabolites can have an enormous impact, both in terms of the physiology. This mouse, for example, is called Portman. It's not going to hibernate, but it's getting close to sleep. So that's now being translated clinically. So people are now being given the berry extract to try and improve cardiovascular health in the human population. This is an early story, but I think in time we go back to that Hippocratic concept of getting food for health. We've tried this as well. So someone who works in aging is now stepped into the world of trying to manipulate the microbiome. And we're not trying to do that by giving people specific good players, so specific nutrients. We're trying to manipulate the community in the gut, but you've got to think of your microbiome as a community. And we're using a prebiotic, so a thing called inulin. It's a resistant starch that you find in garlic, you find it in onions, you get a lot of it in Jerusalem artichokes. These guys get it in a cookie, and there are people that have got renal disease, and they're on hemodialysis. And if you're dialyzing, your chance of surviving 10 years is 10%. 50% normally die in the first 3 years. It's not pleasant at all. Just like having a metastatic cancer. And the idea is that if you can manipulate the microbiome, you might be able to activate more NRF2 and therefore give these people a better chance of making it like 10 years, by which stage they might get a kidney transplant. Currently, 1 in 7 people get a kidney transplant on a waiting list. So it's very hit or miss for them. So you've got to buy the time. And what we've found, ignore the details of the slide, that simple intervention for 4 weeks can increase the number of salutogenic bacteria. So the lactobacilli, the lactospiraceae, the coria in their guts. It also enhances the levels of the bugs that actually make anti-inflammatory compounds, so short-chain fatty acids are good. But they can also activate NRF2, and for us, that's a big thing. And more recently, we've tried to do this again independently in a double-blind, randomized, controlled clinical trial. And we've used another polyphenolic mix of compounds from beeswax, and it's called propolis. And that trial, we've now published, has been successful. It's in a small number of patients, it's about 70. And again, these are all peritoneal dialysis. It's another type of dialysis, which is equally as effective as hemodialysis, but because you're having a line not going into your arm, but into your peritoneum, the risk of infection is greater. So we are seeing an improvement here in terms of the levels of NRF2 and a reduction in the level of inflammation. So we're back to this concept of food as medicine. So I'll finish just by saying manipulating our exposome would be good. That can be done at a lot of different levels. So I play at a level that really is physiological and nutritional, but that really needs pushed out into the social environment and your geophysical environment. I love that you've got the picture here of the Bosco Verticale in Milan. It's a building, car block covered in plants to remove pollution locally from the air. Because, as I mentioned earlier, air pollution is a major driver of aging and mortality. And simple local measures can really enhance your age-related health. And this kind of approach across the city, I think, would be absolutely fab, but that's just me saying that. The knock-on effects for us, of course, are in the planetary health. We have to do something to maintain the environment that we live in and not destroy it. And there are very simple steps that do not require sophisticated technology or sophisticated scientific approaches to do that. We have the tools. I think most of what we would suggest are simple no-brainers. It's just educating a population and getting people to comply. Anyway, I will finish then with Hippocrates again. Give every individual the right amount of nourishment and exercise. Not too little, not too much. We would find the safest way to health. And I'll take questions. Just acknowledge the groups here about the Karolinska Institute and Japan and the US that we collaborate heavily with. Thank you.